Let's talk about time-space complexity. No, for real, it's not as scary as it sounds. It's essentially what we use to measure the performance of an algorithm, in both the time it takes for it to run and the memory or space that the algorithm requires. So, time complexity. This measures how long it takes for an algorithm to execute. And for simple things like just adding two numbers together, say I have an add function and it takes two input parameters and those inputs are added together, this is a constant runtime. Whereas if we had a kind of dynamic size input like an array, and within that function body we iterated over the array, the function is going to take longer to execute based on n, or how many elements are in that array. And in the worst case scenario where we had to iterate over every element in that array, that algorithm would have a linear time complexity because it scales linearly as the input of the array grows. Space complexity is just how much memory does an algorithm use. For example, if I were to define a couple of variables within my function body, and these were of some kind of constant size or primitive type, I would have a constant memory. Now say I had an input that's an array of size n. In my function body, if I were to assign this array to a variable, that would be taking up linear memory because that amount of memory that I need to allocate now is going to grow based on the array. So again, this would be a case where the amount of memory scales linearly with input size.
So here's an example. We have a simple add numbers function that takes in a parameter a and a parameter b. Now this function is just going to add these numbers together and return them. This is an example of a function that has a constant time complexity and a constant space complexity. And it's no different than if we were to do something like this, right? This still has a constant space complexity and a constant time complexity because we know exactly how much space we need and it's going to be a constant. And we're simply adding two variables together, which is a constant time operation. Now let's go into this find max function. So this is an example of a function that has a linear time complexity and a constant space complexity. So we have our base case here where if array length equals 0, we just return null. Else we assign the max number to the first position in the array. Because initially we can assume that this is going to be the largest number we've seen. And then from there we iterate on the second element in the array. And we try to find the next largest number, if one exists. And then we return whatever value max is at the end of this iteration. This is a constant space complexity because the only variable we're assigning is max. So even though we are assigning max more than once, potentially, we are storing a primitive number type there. And why is the time complexity linear? Well, if we hit our base case, we actually run this method at a constant time complexity because length is a constant time operation. But when we calculate time complexity and space complexity, we always calculate it based on the worst case scenario. So in our worst case scenario here, we may have to iterate over all the elements in the array. So that is the reasoning for this being a linear time complexity, because as the size of this array grows, the performance of this function degrades, and it does so linearly. Next, let's move on to this filter numbers method. Now this has a linear time complexity and a linear space complexity. So filter numbers takes in an array of parameters, and then with these parameters we use the array filter method. And for each element, if the element is less than 100, so we're assuming these are all numbers, we want to return a new array with those elements. Let's talk about the time complexity. So the time complexity is linear, because as the size of my input grows, this function, again, the performance degrades linearly, because it's a very big difference working with an input size of 10 versus 100 and 1,000 and 10,000 and so on. This has a linear space complexity because filter will return us a brand new array, and it will return us an array of dynamic size. So in the worst case scenario, it returns an array that's the entirety of the input. And again, when we're calculating time space complexity, we always go based on the worst case scenario. So that is why the space complexity here is O of n, or linear. Now let's go to a different function. Now this function is not particularly useful, but I'm going to demonstrate something here. Now the time space complexity of this function, you might look at it and go, why does it have a linear time complexity? We're simply assigning the input to this variable and then returning it. Right? Seems pretty straightforward. At best, you would probably assume, it has linear space complexity, right? Because these parameters can be of any size and we are creating a brand new variable of it. So we are allocating that dynamic size in memory. However, this spread operation of our input is actually linear time complexity, because this is effectively copying over every element of that array. And as the size of this array grows, this copy is going to take longer. It's going to degrade. So that's just something to think about. Just because we're not using a loop within our function body does not mean our time complexity will be constant.